Okay, so that warm-up example introduced us to this important idea of an area function. And it's so important, actually, that it shows up in the fundamental theorem of calculus, which has two parts. And the first part says that if we define a function, g of x, as one of these area functions from any starting point up to a variable x of a function f of t dt, then the derivative of g of x is actually equal to f of x. So if we started with any function f of x, we could define this area function to actually get an antiderivative of f of x. The way we'll probably use it more, or the way we actually use it more in examples or in exercises, is to write it this way, where the derivative of this g of x function, not even using the notation g of x, the derivative of this area function is actually equal to just f of x. So is equal to the function inside of the integral with just x plugged in. Okay, so this seems like a weird theorem to be the first fundamental theorem of calculus, but actually this is really important because if we have any function f of x or f of t, we can actually define an antiderivative using this definite integral that we defined as, the limit of all those areas of rectangles. So the big reason why the first fundamental theorem of calculus is important is it says that actually an antiderivative exists. We can write it as this area function, which again might be really hard to work with if we only can write it as the limit as n goes to infinity of those Riemann sums. So again, the big reason for having the fundamental theorem of calculus. Part one is that it says that an antiderivative exists. Okay, now finding it might be a little bit harder, and that's a big focus of this class is learning methods to find antiderivatives. But there are still antiderivatives for some functions that seem like they should be pretty easy, that we don't actually know how to write a nice algebraic rule for it. Number two is exactly the evaluation theorem that we had in the last section. And this is obviously a really important theorem that we got. We've been using it already to find area under a curve. And in general, it's important because it tells us an application for antiderivatives or why they're important. Okay, so the main part of this section is just to introduce the fundamental theorem of calculus and talk about why those theorems are important. The only types of exercises or examples that we'll get from this section is actually just kind of trickier examples. So they've got to be set up a certain way. It has to always be taking a derivative of one of these area functions. And it's only in this situation that we apply this fundamental theorem of calculus part one. And it's just kind of a check to make sure that you know what that first part says. So let's go through these examples. So for the first one, we're looking for the derivative of this g of x function, which is pretty clearly an area function like we've had before. So I'm going to write it out in a little bit more detail than you'll probably need to. I'll say how you can write it at the end here in order to write a little bit faster on your homework. So we're looking for the derivative, d dx, of g of x. So just using our definition of g of x there, that's the derivative of the integral from 2 up to x of t squared sine of t dt. So just to match this up with the notation that we were using for that first fundamental theorem of calculus, the f of t that we have in that theorem would be this t function that's inside of the integral. So it would be t squared sine of t. And then just for some notation, I'm going to let big F of t be an antiderivative of little f of t. Okay, and then continuing from there, our derivative of the g of x is going to be the derivative of this integral, but if this is little f of t, then if we evaluate this integral, that would be its antiderivative, capital F of t, evaluated from 2 up to x. And we can calculate this by plugging in x first, so it'll be ddx of capital F of x in first minus capital F of 2. And then, once we take this derivative, then the derivative of capital F of x is just little f, since it's an antiderivative. But of x now, since we're taking the derivative with respect to x. And then the derivative of capital F of 2, well, that's just a constant, so that's not going to give us anything. So we'll end up getting just little f of x out, which would just be f of t with x plugged in instead of with t plugged in. So that t ends up being kind of a dummy variable, and we end up getting x squared sine of x as the result. And you might be thinking, well, we have an integral in here, why don't we have a plus c? It's because we're taking a derivative of that integral. And also, this is a definite integral, so we don't have a plus c in the result. So that constant kind of gets knocked out when we're subtracting this, and then, of course, when we take the derivative. So, okay. All right, so the way that I would actually write this, if I was going to do this as one of my homework problems, is just from this first part. And then right from here, we can see that we're taking the derivative of an area function where we have a constant as kind of the a value in the first fundamental theorem of calculus. And then the x is the top limit of integration, just like the first fundamental theorem of calculus. So just from this and using the first fundamental theorem of calculus, this derivative is just going to be this integrand with x plugged in. So you could actually just jump right to x squared sine of x as the result. Okay. All right, so then for the second one, again, I'm going to do this one kind of longer and then show the short way. We're looking for, again, d dx of h of x, which will be d dx of the integral from 1 over x up to 5 of arctangent of t dt. So this one's a little bit strange. We don't have the variable as the top limit of integration, and we don't even just have a variable. We have another function as that bottom limit of integration. So I'm going to go through this one kind of the long way like I did before, and show what happens when we do this as a derivative. So let's again just set up the notation like we had in the fundamental theorem of calculus. Have f of t be arctangent of t. And again, let a capital F be a antiderivative of f, so f prime of t is equal to little f of t. Capital F prime of t is equal to little f of t. That's just a quick way of saying that it's an antiderivative. Okay, so then we can write this as the derivative, and then again, if our antiderivative of arctangent of t is just capital F, this will be the derivative of capital F of f minus capital F of 1 over x as a value. Sorry, I meant to write this as capital F evaluated from those two first. So let me just backtrack there a little bit. Capital F of t evaluated from 1 over x up to 5. So that would be the derivative of capital F of 5 minus capital F of 1 over x. Bracket. Big one. And now when we take this derivative, it is kind of the same as what we were doing before, but now the constant is first. So that constant will drop out, and we'll end up with negative derivative of capital F. Leave the inside function the same, though. We're using the chain rule here. So little f of 1 over x. And then we still need to use the chain rule, though, to take the derivative of this capital F of 1 over x. So we've got to multiply by, now be careful here which way you're going. We're taking the derivative. So we've got x to the negative 1, so we can actually decrease the power by 1 and get x to the negative 2. And then also bring the negative forward. So it would be negative 1 over x squared as that derivative for the chain rule. So putting all this together, the negatives will cancel. And our f was just arctangent of t, so we'll have arctangent of 1 over x. Divided by x squared, and the negatives canceled. Okay, so in general, we can actually do this a little bit faster, and that's using some of the rules that we have about integrals. So again, this is kind of a setup for why it comes out that way. Let me go over kind of a faster way to do it. Okay, so we can actually flip this and take the negative. So this would be the same as d dx of negative integral from 5 to 1 over x of arctangent of t dt. And now this is more set up as a problem that we could use the first fundamental theorem of calculus for. So the negative is going to come along for the ride when we take the derivative. And then if we were going to take the derivative of just 5 up to, let's say, x of arctangent of t dt, well, that would be just arctangent of x. But instead of having just x up here, we have 1 over x. So we're going to have to use the chain rule. So we'll get arctangent of the inside function again. So if this were an x, again, we'd plug in x. But this is 1 over x, so it's arctangent of 1 over x. But now we need to multiply by the derivative of 1 over x, because we have a composition of functions. We need to use the chain rule. So again, bring down the power. So we'll get negative 1 over x to the negative 2. So, or x is to the negative 2, so over x squared. And again, the negatives cancel. And we can write it as arctangent of 1 over x divided by x squared. Okay, so try some of those examples using the first fundamental theorem of calculus, or some of these exercises. And I'll post the solutions to these exercises, hopefully tonight, but if not, when I get back on Wednesday. So you can check your solutions to them. But there are also problems in the book that I think are odd that you can check. So if you want to try them and then look for them in the book and then look at the solutions, you can. But I'll also post the solutions here soon. So okay, so that's it. Look for the solutions posted either again tonight or on Wednesday after I get back. So, all right.